So the 1 centimeter long string vibrates with a fundamental frequency of, so F, the fundamental frequency, which is F1. F1, we are told, is 256 hertz. 256 hertz. And then the length of the string is 1.0 centimeter. If the length is reduced to 1/4, so L1 is this, L2 is equal to 1/4 centimeter. Keeping the tension unaltered, the new fundamental frequency would be, so if we keep the length unaltered, what will be the new fundamental frequency? So I'm letting this be the new fundamental frequency. Now I'm not writing F2 because F2 would mean that it is the second harmonic or loop, but it is still the first. But the only difference is that we are changing the length of the string to see its effect in the frequency. Now F is equal to F1, or Fn generally is given by n over 2L, or n times V over 2L. Okay. We were told that the tension is kept constant and all that, meaning we have to change this to V to T over the linear density mu. And here we'll maintain this. So we are talking about a certain length of the string. Okay. The linear density, the mass per unit length of the string is constant. We are told that the tension in it is also constant. So T and mu are constant. So if T and mu are constant, then F is just inversely proportional to the length. Okay, so F1 will be directly proportional to 1 on L1. F1 prime would also be inversely proportional to L2. So if we take F1 inverse on F1, it will be equal to L1 on L2. Therefore, F1 star would be equal to L1 on L2 times F1. What is L1? L1, we are told, is 1 centimeter. 1 centimeter divided by L2. L2 is quarter. So 1 on 4 times F1, which is 256. Therefore, if we vary the length, the new fundamental frequency would be equal to 4 times 256. And class, what is 4 times 256? What is 4 times 256? Anybody who got that?
1,000.
Okay, so that's the answer. Okay. All right. The second question, it's still on the platform. The second question says that a stretched string A stretch string, which is 1 meter length and has a mass of 0.005 kilogram, is having a tension of 20 Newton. If it is plugged at 25 centimeter from one end, then it will vibrate with the frequency of what? So try this in about 3 minutes time too. A stretch string of length 1 meter and mass 0.005 kilogram is having a tension of 20 Newton within. If it is plugged at 25 centimeter from one end, then it will vibrate with the frequency of. So we are calculating for the frequency. But mind you, here you do not know the particular harmonic or number of loops that will be formed. So you must calculate that and then use this tension formula of frequency, tension, blah, 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 thing to come. So in about 3 minutes time, just go through it and make me proud. Start with. Okay. Question 3. Question 3. The velocity of waves in a string. Okay, Samuel, I'll record it. I'm recording the video, so I'll send it to the group. Today the network has really been bad. Myself, I've had equal a share of the same problem. So the velocity of waves in a string fixed at both ends is 2 meters per second. The velocity of wave in a string fixed at both ends is 2 meters per second. The string forms a standing wave with waves with nodes 5.0 centimeter apart. It forms a standing wave with nodes, successive nodes. Okay, successive nodes, which is 5.0 centimeter apart. What is the frequency of vibration of the string in hertz? What is the frequency of vibration of the string in hertz if it forms stationary wave with nodes 5.0 centimeter apart and the velocity is 2 meters per second? Start with 5. This one, 3 minutes must do. 3 minutes must do. Start with. The trick is that once you are given velocity of sound is given by F times wavelength. And we are looking for F. Okay, V on lambda. Once we have V, if we manage to get lambda, we'll be excelling. But then, start there, it forms stationary waves with nodes which is 5 centimeter apart. And we know from node to node is equal to a wavelength of half lambda. So it implies that this wavelength of half lambda is equal to a distance of 5 centimeters. Therefore, the wavelength is equal to 10 centimeters. Okay, lambda, when you multiply through by 2, is equal to 10 centimeters. So if lambda is 10 centimeters and 10 centimeters is equal to 0.1 meter. Therefore, frequency would be equal to velocity, which is 20 meters per second, divided by wavelength of 0.1. This is meter per second. So we have, okay, 20 divided, the speed is 2.0. So 2.0 divided by 0.1 is equal to 20 per second. And 20 per second is the same as 20 hertz. The reason for which I said this is a little, just a small trick. When you understand that, or you are able to recap that the wavelength from node to node is half lambda. So if half lambda, please, any question? Any question? No question. All right, let's look at formation of stationary waves in pipes and tubes. We are looking at applications of stationary waves, and we've done that for vibration in string instruments. Let's look at pipe, open pipe, and closed pipe. So resonance or vibration or formation of stationary waves in pipe has to do with two closed pipes. We have the closed pipe and open pipe. Open pipe. So let's pick them one at a time. Resonance in closed pipe or tube. You later understand why this is being termed as resonance. Okay. What do we mean by resonance? Resonance is said to occur whenever one oscillating body or vibrating body, one body vibrating at its natural frequency affects the frequency of vibration of another. Okay, so as we speak, we are heard due to resonance. When you speak, your vocal cord, that thing which is here, okay, vibrates. So when you speak and you put your hand here, you feel a vibration of your vocal cord. Once it vibrates, it is vibrating at its own frequency. Now the air within your the canal, this canal, trachea, respond to the vibration of your vocal cord. And when the air within your trachea around the mouth respond to the vibration of the vocal cord, frequency resonance is said to have taken place. And whenever resonance occurs, every resonance occurring is characterized by production of loud sound. So the sound which comes out from our mouth depicts this situation of occurring resonance, where one body vibrating at its natural frequency affects the frequency of vibration of another. Okay, so in closed pipe and then open pipe, once that action where air is blown into the pipe or tube and there is that production of loud sound, we term that as resonance. Hence, resonance in closed and open pipe. Application of this is the usage of this wind instruments, trumpets. So applications of this can be seen in here. We are talking about closed pipe. So trumpets, in trumpets, adwa otubias trombone. Trombone. Then saxophone. Saxophone. What again? Closed pipes. Trumpets, trombone, saxophone. Do you have any more examples? Anyway, I've given you 3. Look for them. And here, this one applies to all musical instruments that is played by having one end closed with the mouth and then having the other end open. Hey, Nana, and your example, tuba. Wow. The next example, awesome. Okay. Tuba. Last time you also gave me some other examples. Anyway, when we get to them, then you bring them up for us. So this, we are referring to all instrument that is played by closing one end with the mouth and having the other end open. Is that okay? So we have a tube or pipe of length. I think the pipe organ, also falls under this category. So in closed pipes, we have one end open and the other end closed. So when air is blown, full trumpet, those trumpets appear. Charlotte, are you there? Charlotte. Oh, she's gone. So we have pipe or tube of length L. When you blow air into it, okay, the air blown into it responds to or is blown according to the frequency of vibration of your vocal cord. Now, the air blown into it causes a disturbance of the air within the pipe and they resonate. When they resonate, frequency is said to have taken place. So resonance is basically when one vibrating body catches the frequency of vibration of another. Resonance in sound, I mean. Okay. When one body vibrating at its natural frequency affects the frequency of vibration of another body. Resonance is then said to have taken place. So that's the meaning of resonance. Whenever one body vibrating at its natural frequency affects the frequency of vibration of another body, resonance is then said to have taken place. Okay. Occurrence of resonance is always characterized by the production of loud sound. So whenever resonance takes place, whether resonance in electrical circuits, resonance in sound, okay, or mechanics, it is characterized by the production of loud sound. So you could hear me due to resonance. When you speak to your brother or mom or dad and he or she can hear you out, is due to resonance. You can watch TV, um, um, TV, or you can catch a particular television station due to resonance. You can catch any nearby FM station due to resonance. So we have resonance in electrical resonance, resonance in AC circuits, and also this is about resonance in sound. All right. So we have a tube of length L. Air is blown into it, as in playing trumpets, trombone, saxophone, or whatever. Air is blown into it. Keyboard, you see, keyboard, you are pushing in a certain force on the key. So the force, okay, causes the resonance, the air molecules or particles within the pipe to resonate. So as you press on the keys, okay, you are causing a vibration of the material or whatever is used in making that white and black keys. Okay, now you want the air particle within the pipe underneath to respond to the vibration of your hand. And once that happens, resonance, and it is connected to electrical something which will augment the sound. Boom, 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 boom. So as you do this, that's what happens. Okay, so this time air is blown into it. Now, for closed pipes, because one end is closed, one end is open, there's formation of nodes at the closed end. And there's also formation of antinodes at the open end. So the stationary waves or the loops that will be formed within the tube.
Please don't clean it.
Don't clean it, don't clean it. Yo, I've left you something. Finish hard.
I can't see.
And then I can give you the video. Okay. So for all stationary waves, it is just two progressive waves in opposite directions that interfere. So if we have closed end and an open end, the kind of stationary wave that will be formed. So we always pick our drawing from a progressive wave. Because this end is closed, there will be node here. So the first possible node or loop that will be formed would have this shape, closed and open end. So the first possibility will look like this, just this, and this will be the reflection. So one is the incident and then the reflection. So if you have a tube of length this, the first node or loop that will be formed will look like this. Will look like this. If the wave exactly fits the length of the tube. So a node here, an antinode here. So a node here, an antinode here. Don't forget, we are always picking our drawing from progressive wave. So that's the first possibility. First possible stationary wave. Boom! Well, when the air is blown into it, that continuous sound you hear, boom, are of series of notes or loops. The first possible loop or notes that will be heard would have a shape like this. Now, we always know that stationary waves are formed with a particular wavelength and frequency. So we'll go through to find out the wavelength which forms this and its accompanying frequency. Any question? All right.
Please.
Now, what is the, if this is node antinode, in terms of wavelength, what will be the wavelength of these nodes? From node to antinode, what is the wavelength of this stationary wave? Yes. Anybody to help? Quarter what?
Wavelength.
So 1/4 lambda. Thank you, Amma. Therefore, lambda will be equal to 4L on 1. So this becomes the fundamental wavelength. Fundamental wavelength. Of course, the stationary wave also becomes the fundamental notes. Fundamental notes. So if this is the fundamental wavelength, lambda 1, what will be the fundamental frequency? Yes. Because it produces sound, that we want to determine the frequency of the sound that will be produced by these notes. So F1 being equal to velocity of sound in air divided by the fundamental wavelength, lambda 1. F1 therefore is equal to V over 4L. This is the fundamental frequency. Fundamental frequency or the first harmonic or zero overtone. Let's determine subsequent notes. Subsequent notes, F2, lambda 2. Now, the second possible note that can be formed will be close end node here. The second would override the first. There is formation of antinodes at the open end. So this will be the second possible node that will be formed. And when you are drawing, add aesthetics to it. So the second note or loop has this shape. So L length of the tube, what will be the the wavelength of the note? What is the wavelength of the note? Class, what's the wavelength of this note? Hey, no one is talking. Class,
Lambda.
do not waste time. I beg you. This is AA. So 1, 2, 3. So we have 3 of the quarter lambdas. From node to antinode, quarter. Antinode to node, another quarter. Node to, and so we have 3 times quarter lambda, which is 3/4. L is equal to 3 lambda. So lambda 2 is equal to 4 L on 3. L on 3. Therefore, F2, which is V on lambda 2, would be equal to 4 V divided by 4L times 3, which is F2 is equal to 3 times, this is F1. F1 is this. So if F1 is this and F2 is equal to 3 times this, then it means this part is equal to F1. Okay. So this is 3 times F1. 3 times F1. The third note will look like, so first, second, the third would also continue like this and here. And so the reflection F3 will also look like this. So let's clear this one and then push in F3. Same length. So we have 2 loops before the last end. Let's draw, add beauty. I think we have the same thing. Okay, that's it. 1, 2, 3. So what will be the wavelength? What will be the wavelength of this note?
5.4 lambda.
Okay, so 1, 2, 3, 4, 5. 5 on 4 lambda. Yes. Therefore, lambda 3 would be equal to 4L on 5. Then F3 would also be 5 times V on 4L. which is equal to 5 times F1. So the observation is that here F1 is actually V on 4L. Then F2 is equal to 3 times V on 4L. Then F3 is equal to 5 times V on 4L. So we realize that the harmonics are odd. 1, 3. Okay, the coefficient 1, 3, 5. The next one will be 7, 9, and so on and so forth. So closed pipes have odd harmonics. Closed pipe have odd harmonics. Okay, what do you think will be the frequency of the nth harmonic? What will be the frequency of the nth harmonic? Fn. Anybody to help? The frequency of the nth harmonic. If the harmonics are odd, Amma.
That is, I think, n on 4L times V.
N on
4L.
4L times V.
V.
Let's see. If N is 1, we'll have V on 4L. It fits the first one. If N is 2, we'll have V on 2L. It doesn't fit this. If N is
The N
if N is
can it be plus 2?
pardon?
Can it be N plus 2?
I just want to try what you are saying. So we get that N plus 2. N plus 2 over 4L times V. Amma, is that what you are saying?
Please, it was not me. It was, I don't know.
And this is your view. Let's try it will work. So
Mistake.
Amma,
Please, it was someone else who spoke.
let's try. Okay. If N is 1, we have 3 on 4LV. 3 on 4LV, which fits the second one. It doesn't fit the first one. If N is 2, so N is 2, we'll have V on L. It doesn't fit. So it means this one too will not work. Any other view? The nth harmonic. Annalyn is suggesting 2n minus 1. Okay, V on 4L. Let's see. Let's look at Annalyn's suggestion. See, 2n minus 1 V on 4L. Okay, as an nth harmonic. So if n is 1, we have V on 4L, which is true. It fits the first one. If n is 2, we have 3 V on 4L, which is right. If n is 3, 5, so this is correct. So it means that the nth harmonic is equal to 2n minus 1 times this, or Fn is equal to 2n minus 1 times F1. This will be the expression for the nth harmonic. So for closed pipes, this is the expression for the nth harmonic. Please do not forget harmonics and overtones. Okay, the first harmonic is the zero overtone. The second harmonic F2 is the first overtone. The third harmonic becomes the second overtone. The fourth harmonic becomes the third overtone, and so on and so on. So this is it for closed pipes. This is it for closed pipe. Now, the nth wavelength. The nth wavelength. You see, lambda 1, we saw that lambda 1 is equal to, since L is equal to quarter lambda, we had lambda 1 being equal to 4L on 1. Then lambda 2, we got 1, 2, 3. L is equal to 3 on 4 lambda. So lambda 2 gave us 4L on 3. Lambda 3 also gave us 4L on 5. Therefore, the nth wavelength would also be 4L on 2n minus 1. So that if n is 1, we have 4L on 1, which is this. If n is 2, we have 4L on 3, and it's also fixed. So this is also an expression of the nth wavelength for closed. Please, any question? Before we look at the open pipe. All right. Charlotte, do I clean the board?
Yes.
For open pipe, here we are talking about instruments such as what's the name of this instrument? Nana, give me examples of instruments that fall under this category. Nana, open pipes. Open pipes or tubes. Nana, any example? Okay. Nana may come later, but we have the flutes. We have the flutes. We have the harmonica. So, any instrument with two ends open. With two ends open. So here, if we have L length, of the tube, for L length, the notes or the station wave formed is always drawn from this. Now, because there are open ends, there will be formation of antinodes at both ends. there will be formation of antinodes at both ends. So the first possibility, here we are starting from an antinode and ending with an antinode. So the first possibility will look like this. The incident must look like this. And then the reflection must also look like this. Of course, they must have the same amplitude. So when you are drawing it, you bring so this is the first fundamental note. The fundamental note or the first possible stationary wave. So what is this? The wavelength which forms this. L is equal to, yes, Charlotte, what will be the wavelength of this note? Charlotte, are you there?
Yes.
What will be the wavelength of this note?
Half lambda.
Okay, so quarter, antinode, antinode. So quarter, another quarter. So how? Lambda. Therefore, lambda 1 is equal to 2L on 1. Okay, so fundamental wavelength. The fundamental wavelength. F1, which is V on lambda 1, is also equal to V on 2L. This is the first fundamental frequency or the first harmonic. Please let me repeat that for vibration in pipes, it has nothing to do with V. The V has nothing to do with this T on mu. That is why I said that this is velocity of transverse wave in strings. For strings, we can load it or connect mass to it so as to tighten or produce a tension in the string. But this is just blowing air into pipe. So please, this V is velocity of sound in air. And velocity of sound in air, this is sound is longitudinal wave. So this V is velocity of longitudinal wave in air. Okay, so this has nothing to do with tension and linear density. So please let's take note of that and then get the difference. So this becomes the fundamental frequency or first harmonic. The second note would also look like the first is this. The second will continue and end here. And then the reflection would also look like this. So the second note would also look like this. One complete. It will look like this. So if length is this, Amma, what will be the wavelength of this node? Amma,
Yes, sir.
what will be the wavelength of this node?
Lambda.
So let's see. Quarter, 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 quarter. So 1, 2, 3, 4. Good. So 4 times quarter lambda. 4 times quarter lambda. Therefore, this will be equal
Say,
to.
dear.
Hello.
Pete, how are you doing the counting?
Okay, so this is antinode. This is node. This is antinode is here. So once this is antinode, this is a node. This is another antinode. So I'm counting antinode to node, node to antinode. So 1, 2, 3, 4. Anytime I see either N to A or A to N is quarter lambda. So antinode to node 1, node to antinode 2, antinode to node 3, 4. Charlotte, are you okay?
Yes, please. Thank you.
So lambda here is equal to 4L on 4. Is that 4L on? So lambda is equal to where is the first one? The first one is this. Okay. Okay, so it will be 2L. That's not wrong, but we want to create it to look like this. So 2L on 2. So if this is lambda 2, if lambda 2 is this, then F2 would be equal to V on lambda 2, which is V on 2L times 2. So we realize that F2 here would be equal to 2F1. 2F1. Okay, let's draw the third one and then generate the end wavelength. So the third note would continue and end here. So the reflection would also look like this. So this time we have 2 completes within 1 complete. This is 1, 2, and then the quarter. So if we have this length, of 2, we have hey, 2 complete, we are going 3. Okay, so we must end here. So when you use the progressive wave to guide, in fact, the drawing becomes easier. Okay. So let's count to determine this is antinode, node, antinode, node, antinode, node, and then antinode. So Charlotte, I'm counting again. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. So 6 times quarter lambda. So I have L being equal to 3 on 2 lambda. So
Say, dear.
Hello.
Please, when I counted, I got 7.
Check well. Oh. This is that we are always starting from a node ending. So first one, second one, third one. Good. So antinode, node, antinode, node, antinode, node, antinode. So 1, 2, 3, 4, 5, 6. You should get 6. Check well. You should get 6. So lambda 3 would be equal to 2L on 3. 2L on 3. Therefore, F3, which is V on lambda 3, is also 3V on 2L. 3V on 2L. So clearly, this is equal to 3 times F1. So if we look at the harmonics for open pipes, we have F1 equal to V on F1 equal to V on lambda 1, F2 equal to 2. I'm coming. Oh, okay. V on 2L, F2 equal to 2 times V on 2L. Then F3 also giving us 3 times V on 2L. So you could see that this is also a mixture of odd and even. Okay, this is also a mixture of odd and even. F1, 2F1, 3F1, the next will be 4F1. Therefore, the nth harmonic, Fn, is also n times F1. This is odd, a mixture of odd and even, similar to what we saw in strength, vibration in strength. And because of this, practically, what it means is that for closed pipes and open pipes, for closed pipes, the frequency is odd. So assuming the first frequency is 100 hertz, for closed pipe, I mean, the second frequency you hear is 300. The next frequency to receive 500, 700, 900. This is odd harmonics. This one gives us that continuous. So if for open pipes, if the first one is 100, the next one is 200, 300, 400, 500. Practically because of this, sounds coming from open end instruments has that quality or has that sweetness to listen than sounds coming from closed pipe. Compare the sounds from flutes and harmonica, what we call as mouth organ, and then the sound produced by trumpets. Okay, you see that, or you could attest to the fact that sound produced by flute has that sweetness to listen to compared to sounds coming from closed end instruments. If you've been so observant, you understand this thing. So that is that practical application of this. this has this continuous frequency. Okay. So if the first frequency is 100, okay, there is that continuity. Ooh, 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 in that order. As for close and ooh, 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 there's that discontinuity in the sound produced from instruments. So that's it. Any question here? Any question with regards to whatever we've done? So please, what you must understand is that open pipe or tube instruments have that continuous frequency. Please spend time to go through this. Go through whatever we derive for closed pipes. Okay. And then, as usual, within the week, I'll send questions. I'll send questions so that you try your hands on. The next thing we must do is application of closed pipe, which is in resonance tube. Resonance tube experiments. Okay. So that's the only part we are left to do. Then we'll look at, apart from after treating resonance tube experiment, then we discuss Doppler effect, which is also another small part. Then we can start another topic. Okay. So if you have any question, Ama and Co, ask. Charlotte, Lizzie, Festus and Co. If you don't have any question, then this is where we draw the curtains on today's meeting. Okay. I'll forward your work set. I beg you, spend time and do it. Okay. All right. So see you next week. Take care of yourselves and bye-bye.
Bye. Ethiopia.
Yeah, man.
Ethiopia, see the yesterday what we were doing,
Yeah.
the work we were doing,
Mhm.
the do that was equal to math online. Why were you still looking from you since you gave it to us in the question?
No, it was an oversight. I did not see it. Though I was reading the question, but my attention never came on that. Is that okay?
So
So
since the question gave you, we can use that one, right?
yes, F it's one it's about the fundamental frequency. So 1 on 2L T on mu. What I saw was that the question actually gave us mu. The reason for which it was 0.001 kilogram per meter. Okay. So what we were given, I think it was expressed in standard form.
Yes, please.
Yes. My attention never came on this. I felt whatever was given was mass. The reason for which I was using this and then dividing by 0.5 or so. But what we were given was actually this mu. So that is, you must substitute this into it straight away. Okay.
So Mr. Ethiopia, if let's assume the mu was mass, so if we were using the formula, this formula, we would have converted the mu to mass on length. So would the formula be 1 on 2L root T times L over M, or it should just be T on M?
I don't get your question. If what?
So everything, yes, you were saying that if length is equal to 1 meter, then mu will be equal to meter. So let's assume this mu was mass instead, and it was 0.001 kilogram. So would the formula be T times L over M, or just T on
If
M?
this is it, and the length of the string is 1 meter,
Mhm.
then in this case, mu will just be equal to M. So
Yes.
mu would have been 0.001 kilogram. I think even today
Okay.
we solved
So the formula was
come again.
so say if we assume that mass was the 0.001, would the formula be T times L over M or just T over M?
It will be 1 on 2L times T over M. Because mu is M.
Why would the
Why would
Exactly, the length you get was 0.50, which is not equal to 1. So why won't we multiply the tension with length, but instead write tension over M?
is it a different scenario? If you earlier gave a scenario that if this is mass, okay, if M is 0.001 kilogram and the length is 1 meter, is that not what you earlier asked?
No, and the length was 0.5.
So if the length this time is 0.5 meter, then you must look for mu. Mu would be equal to M over L. And so 0.001 divided by 0.5 would be the linear density.
Okay.
So,
Okay, so
so whatever you get for this is what you substitute in place of mu.
okay. Okay. So please, last question.
Okay.
So please, so if L, see the original formula is if mu was M over L, the original formula would have been 1 on 2L with T times L over M, right?
Hold on. If mu is M over L,
M over,
mhm,
the formula will be M equal to 1 on 2L times root T times L over M, right?
exactly. But don't forget this.
Uh-huh.
This will happen if L is not 1 meter.
Okay. 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 Understand now.
Okay. Okay. Bye
Thank
bye.
you.
Bye bye then.
Bye.
Okay. Agua Watma.
It's Adria.
So you've been here all the while. Stephanie,
Yes.
I was calling you. And Nana, the instrument one. All right. So see you. Okay. Agua, bye bye.
It's Adria. Bye.